I haven't done this in a while. Let's, what do I press? What do I press? Share screen. That's what I need.
I don't want this. Hop off. Just a minute, stay away from me. No, there's a lower class. You take what I do.
All right, here we go. Were you here on Friday? You left like the first 5 minutes.
I didn't.
You left the first 5 minutes of one of the classes.
Yeah, that was Tuesday. It was this class, but it was Tuesday.
Tuesday, okay, I knew. I was close then. All right, so we left off by talking about, we got problems with eyeball observations in astronomy. I mean, there's nothing wrong with your eyes. You have good eyes. The issue is that it's limited. One, you can only stare at the sky for so long. You got to blink. You may see something like the guy who thought he saw canals on Mars, and you may see something. It's not true. There's no way to record other than you making a picture on a piece of paper, which seems quite inefficient, which is how it was done, by the way, until they came up with the fact they could take a picture. But you had to have photography, and that only came around the Civil War, right? A little bit before the Civil War. So all the telescopes, remember, Galileo, Newton, we all had telescopes well before the 1860s. But we didn't have wet photography until right around the Civil War.
Mr. Sheridan, why are you bringing us pizza?
If you keep asking, there won't be pizza.
You only asked once.
I said right before spring break is what we agreed on.
Oh, okay, sweet.
Wet photography works really well. Now, we went into some details about wet photography. It's called wet photography because you got to use chemicals to develop the film. And for astronomers, for those of you who don't know about the wet photography, you have film, literally a piece of celluloid, kind of like plastic, that has chemicals on it. It gets exposed to light and it turns black. Well, what's basically making a negative of what we see? White becomes black, black becomes white. So when you look at these pictures, these black dots here are actually, well, light objects of some sort, mostly likely here stars. The blurriness you see right here is because, well, ancient telescopes weren't that great, or we're looking at maybe nebula, something like that. If you want to see the actual image, then you have to make a print of this. You got to take another photograph of this, and it reverses everything. It's kind of crazy. In this process, you lose some information because you're doing the process twice. And we made a statement that they would take multiple images, therefore they could see motion. And this literally was how Pluto was discovered using this wet photography method, where they would take multiple images, sometimes weeks, sometimes hours apart, sometimes months apart, and they would see if they could see any differences. Now, the reason why the stars aren't blurred or moving because they have those trackers on the telescope. All right. We launched spy satellites that had wet photography inside. I said that, I went this big long story about the process, but the point was that eventually this is a very limiting process, and technology came around and basically solved this problem of wet photography. The fact that it was a physical thing. I literally had to physically move something from one location to the other one. Right now, when we talk about photographs, nobody physically hands you pictures anymore. They hand you your cell phone is what they usually do, right? Well, occasionally, but how often? I mean, it used to be that you literally went to the drugstore and got prints of these things. When's the last time you went to the drugstore and got a print?
Like a month ago.
Right? And you do know you can take you got to have it on like a thumb drive or something like that. You can still go to Walgreens and get prints made of pictures.
Yeah.
All right, so the big leap forward, this is going to take a little bit of time, but it came with this thing called CCD. And in order to explain this thing called CCD, I got to tell you a story. So here is the story, a little bit of history. This is where we left off. These things called vacuum tubes. Nobody asked Mr. Surratt about vacuum tubes.
I asked him about.
You asked him about the Hall of Fame, but you didn't ask him about vacuum
I got
tubes.
to see his hair.
So,
As a performer.
so ask him about vacuum tubes and amps and why they're theoretically better. All right, so there are a lot of things that you do with electronics, chiefly among them is like an amplifier. You want to amplify a signal, make it strong, turn the volume up, right? So you want to amplify a signal. The device that was used for a long time were these things called vacuum tubes. They were basically light bulbs, not necessarily to provide light to something, but do some basic electronic functions that I'm choosing not to tell you about. It's complicated if you want to talk about the things it actually does. It's not important to this story. But anyway, to make electronic devices, say a radio, you needed a number of these vacuum tubes in order to make it work, which is why radios back then were literally the size of your desk that you're sitting in. Like it was a big box full of vacuum tubes to make it work and other things. You open up the back of it and you looked at it, it would look like this big metal thing and vacuum tubes plugged into it. And I told you the story about how, used to be kids would, oh, I can fix these radios. And kind of dangerous. Problems with vacuum tubes, it's a light bulb, right? You drop the light bulb, it breaks. You couldn't like move these things around too much because they were literally light bulbs. They were extremely hot, like burn, like cook bacon on it type hot. Used a ton of electricity, and they were physically large. I mean, this clicker I'm holding in my hand right now was basically the size of a vacuum tube. Some were even larger than this. Some were slightly small, but they were large, right? Cell phone in my hand, vacuum tube next to it. You're not making cell phones with vacuum tubes. The cell phone will be the size of this room, right? I mean, physically, if you to put as many vacuum tubes as you need to make this cell phone work, would probably, I'm probably not even exaggerating enough, but it would have to be the size of this room full of vacuum tubes. All right.
That would work really efficiently.
Guy named Lilienfeld, he was Hungarian, about 1925, he discovers something. He writes a patent for it, but he can't actually make the device. But he comes up with this idea, and everybody says, oh, that's a pretty good idea. He just can't make the device. It took, he pulls out a patent for the idea. It took these three guys, Bardeen, Brattain, and Shockley. Shockley is this guy right here. This is right after World War II. They're the guys that came up with the answer for the problems of vacuum tubes. And here it is right here. And this ugliness right here, you can see it in front of their hands right there. It was called the transistor. A transistor is a replacement for a vacuum tube. We call it a solid state device. It's not made of glass. You can throw it up, stomp on it, and it still works. It doesn't get as hot as vacuum tubes. It does get hot at times, but it's a much, much, much better device. All three of these guys win the Nobel Prize for coming up with this thing. This is greatly enlarged, but this is a transistor. It replaces vacuum tubes. So let's see, it's way lighter. It's not a light bulb. Doesn't get as hot, uses a tiny, tiny, tiny fraction of electricity. Therefore, we can make things smaller and lighter now, electronic things. That's a good thing.
How big is it?
The size of a pea, right? Size of a pea transistor, right? Even a little bit smaller than that. So who needs a smaller electronic device that doesn't use a lot of electricity, that's way lighter? Who needs those things?
I do.
Well, they were very expensive. I mean, we're talking thousands of dollars to make a transistor. Now transistors are less than a penny. So who needs and who doesn't care about the price, but they want something lighter, stronger, faster?
The government.
The government, right? And particularly the military. So the military wants these devices. Why? If you replace, and there used to be vacuum tubes in airplanes and missiles, right? So replace those heavy, needs a lot of electricity. You replace them with a much lighter thing, and guess what? You can carry more bombs. You can build your rockets to go farther and faster. So the military says, I don't care if they cost $umpteen-thousand, I want them. And so this big burgeoning field of making these things called transistors jumps up from creation in the 50s, late 50s and the early 60s, right around the space race time.
Oh, yes, let us spend our money.
Now, as the price of this, since the military is funding this, or the government, it comes down, all of a sudden companies like Sony and Emerson's lost to time, but Sony comes around and says, hey, we can make things that regular people want. Instead of a nuclear bomb, right, or a missile, we can make a radio. A radio, instead of being the size of your desk, now fits in your hand, and it's battery operated. Used to be your radio you had to plug into the wall. Now, literally, I mean, this is much enlarged. It's the size of your hand. bigger than a deck of cards, but basically paperback book
Is
size.
that transistor
Right.
radio?
This is why it was literally called a transistor radio. It didn't use vacuum tubes. It's a little bit hard to see that these little things that are pointed to are your transistors. They're basically the size of a pea. It's still large though, right? It's not a cell phone. It's a radio. That's it. And it's battery operated, and the batteries don't last that long. Okay, story continues. So you got this cool thing called a transistor, revolutionized all electronics everywhere, from cars to planes to transistor radios. Along comes another guy, works at a company you're very well familiar with, right? This guy's name is Jack Kilby. It's kind of a strange looking photo, but that's the one they always show of him. He came up with this ugly mess right here. And what he figured out is, right, well, transistor radio needs a bunch of transistors. Computers need lots and lots and lots and lots of transistors. What he figured out was a way to print, like literally, it's a little complicated, to literally put millions of transistors on a little thin film. He's the guy that came up with microchips, or integrated circuits is what we call them. So an integrated circuit, it's not just the transistors, it's other parts to that radio now I'll get put on the size of a chip, which once again is the size of a transistor, a P, right? You open up the back of any electronic thing, you see these little black things that are kind of rectangular or square shaped. These are your chips, and they have billions of transistors and other electronic devices built into them. And it can be easily repeatable. If Kilby comes up to it, you don't want to know what the first thing he makes with it? It's in your math class.
Power calculator?
He's the guy from Texas Instruments.
Oh.
He came up, he came up with integrated circuit, but the company, Texas Instruments, said we can make a calculator out of this. One of the first things made. That's the guy that you can say thank you, Mr. Kilby, for coming up with integrated circuits.
Thank you.
But pretty smart dude. He gets Nobel Prize as well too. Oh wait, did Kilby? Yeah, he got the Nobel Prize for that as well too. We've had computers for a long time. During World War II, we had computers the size of buildings. Here's a picture of one of the first computers that was in America called the ENIAC machine. And it was room upon room upon room of vacuum tubes. Vacuum tubes turns into transistors, transistors turn into integrated circuits, and that's where we get all the cool devices that we have right now. So that's the story. What does this got to do with astronomy? Little, except for once we had this thing called an integrated circuit, along come a couple other people. Here they are, Boyle and Smith. And what they found is a special type of integrated circuit. Here's a picture of it, right? Inside your cell phone right now is one or even two of these, right? This is called a CCD. And a CCD is a microchip, an integrated circuit that does the following. If you zoom in on this chip right here, you see this grid-like system right here. You get little tiny individual pieces, parts. And what they do is the following. When light hits one of these little, I don't know what you want to call them, rectangles right here, it charges it up and it gives it an electrical charge. And what happens is the computer can, for each one of these tiny little, they're rectangles more than they are squares, when they see one of these, your computer can say, I know what the charge is on this one little tiny thing right here. So light comes in, it strikes this, gives it a charge, which is why it's called a charge. And the second part is called a coupled device. Okay. And what happens is, here's your grid. Now they are squares. And so if no light hits the little square, you get a charge of 0. If light strikes it, maybe it's got a charge of 2. And if a lot of light strikes it, maybe you got a charge of 9. Your computer can read all of these numbers, take it and cut to the chase. Read the numbers, and can you see it?
Looks like Sudoku.
But can you see it? What?
Circles.
It's circles. Look, if it's a bigger number, you get a higher light value. If it's a lower number, 0, you get a black. A 9 is really bright white. this is how your camera and your cell phone works, right? Is it has this thing called a charge coupled device, which takes light that strikes it and turns it into numbers. And those numbers you can turn into a picture, charge coupled device. So write this down.
Oh,
All right.
God.
A charge coupled device is an integrated circuit. So it's one of those things that Kilby came up with, containing an array or links, array of linked or coupled capacitors, which is where the charge coupled device comes
So are
from.
you telling me every time I take a picture, it's just numbers?
It's just numbers.
Oh, God.
Sweet. Man.
I notice I have a period here. That should be a comma, not a period. And that shouldn't be a capital U. It should be a lowercase u. Under the control of an external circuit, each capacitor can transfer its electrical charge to its neighboring capacitor. What it's basically saying is that light strikes this thing, which turns it into numbers, and the numbers can be read by a computer. This is how it works. You're probably familiar with the solar panels on roof, where light gets turned into electricity. So it's not an unknown phenomenon to you that light can be turned into electricity. It's not exactly the same in terms of what it's doing, but it's similar. Light gets turned into electricity. Electricity is read, which turns it into numbers, and those numbers can be further turned into pictures.
So which period is supposed to be followed?
No, I had it right. I screwed up. It should be a period. Charge coupled device, CCD. You'll hear this now from now on, like they'll talk about when they're talking about devices. Oh, it's CCD. They're just talking about the chip on the device, like your cell phone, that actually makes pictures, or takes pictures, I should say. And each one of those tiny little squares we call a pixel, right? A picture element. Pixel. And so they talk about, hey, how many millions of pixels there are on that CCD. Bigger the number, better the image.
Yeah, the one with the Pac-Man
The giant
that ate
Pac-
off the tree.
All right, we okay? Yeah.
How many does average like a phone have?
I don't know. I got an old phone, so I mean, I want to say that the new phones are like, I could be making it 10 megapixels, somewhere around that range, something like that.
It's not like
Right.
that.
Tangent. You asked the question maybe about a month ago. You said, how long does a supernova last? It's somewhere in the range of 60 to 100 seconds, like the explosion itself. So it's really short, really short. All right, so why is this a big deal? Why are we in astronomy class talking about microcircuits and chips and whatnot? It's because this was the answer to a lot of problems that astronomers were having. Compared to wet photography, remember, astronomers are taking pictures, wet photography, of astronomical events. Believe it or not, wet photography only will process 5% of the light hitting the film. No. So 5% of the light hitting the film is what gets required for wet photography. For a CCD, it's 90%, a lot more. So remember, the game in astronomy is more light, the better the image. So boy, does this answer a problem with astronomy. The second thing it answers is it's way quicker. Well, if you take a picture of Mars, you got with wet photography, you have to, you got to literally pull the film out of the telescope. You got to walk to a dark room. You got to develop the film. It's got to dry. It's not instantaneous. Whereas CCD images, we all know, ooh, I could take a picture. Oh, that sucks. Oh, let me take another one. With the old cameras, like literally you took a picture and you prayed it was good. Like, God forbid, okay, when I got married a long time ago, 31 years ago, the photographer would take a picture, right? That was it. You get one shot at it, right? And then they would have to go develop the film, and God forbid if it didn't work, right?
Wait, did they have the big stand cameras when you got
Well,
one?
they still have those. I mean, like photographers still use those.
Yeah, I know, but like.
You talking about the one where the guy's holding the flash powder? No, I'm not that
How old
old. 57 next month. So way quicker. It's digital. Digital means it's numbers, ones and zeros, right? It's numbers, and those numbers can be transmitted nearly instant speed of light to other devices, which is why in your life, when someone takes a picture, it's not that big of a deal. You're like, hey, send me the picture. In my, before this, literally, you were talking about physical objects that had to transfer from one person to the other. The scariest thing now is it used to be your house would burn down, you lose all your pictures. Now, if your house burns down, even if your computer burns down, it's backed up to the cloud, you still have your pictures. If it's digital, that means literally you can send the picture to anyone else in the world, billions of times, and it's the same picture. With wet photography, you either physically mail it to someone, or you take a picture of the picture, you lose some of the image, and right, you lose nothing with digital photography.
But how is the color transfer? Like,
We'll talk about that in a second.
Okay, because it was just the numbers.
Correct, and that's a good question.
Yeah.
If it is digital, we can now image process. We could image process with wet photography as well too. Because digital imagery allows that process much quicker, and you can undo the effects of it. All right, all of these are really good reasons for astronomers to like digital photography, which is why all astronomers now use digital photography, right? It also allows us to send spacecraft like the James Webb Space Telescope far away from us to actually get those pictures. All right, so this is doing some weird things. Let me tell you another story about image processing, okay? So here is, it's not clicking well. There's a country in the world, and that country is called?
That is not Madagascar.
That's Madagascar. What's this country?
Madagascar Part 2.
No. Look at the map.
Egypt.
It's close to Egypt. It's next country over.
Chad.
No.
Look at the country.
Spain is over there. Yeah.
Spain is way over here.
Yeah, I don't know. And then there's Italy.
Somebody rescue me before I think you're all inept in your geography. Wes, you are sitting closest to the map.
Oh, Weston, you idiot. I don't know.
None of you know what that country is? Egypt, Saudi Arabia, Iraq.
Yemen. Afghanistan.
Iran.
Iran is right here.
Is it Qatar?
My dad's been to Iran.
What is, it looks like this.
Dagger.
This country is always in the news. Always in the news.
Uzbekistan?
Israel, thank you.
That's not.
I didn't hear you.
Yeah, no, that was something.
I couldn't
That's
tell if it was
Israel.
like Iran or like.
All right.
I thought it was
All right.
I thought Israel was-
Let me tell you a story about Israel and what this has to do with astronomy.
A sheet of glass. It's so easy.
Israel, here's a blow up of Israel. Israel has a place called the West Bank. And the West Bank it's called the West Bank, bank of the river. The River Jordan is right here. So it's on the west side of the River Jordan. That's why it's called the West Bank. And there's a sea here called the Dead Sea. You've probably heard of it. Okay. Dead Sea is called the Dead Sea because it doesn't drain in anything. It's very salty, and you always see pictures of a strange thing. It's this, I don't know if it's the saltiest sea in the world, but it's one of them for sure. And when you literally people, you can't walk on it, but you see people floating on it, it doesn't look right. Right.
There are no fish in the Dead Sea.
All right. In the Dead Sea or the Dead Sea area, it's mountainous around it. And through various devices of geological activity, wind, erosion, weathering, you get caves that appear. Okay. And for those of you who know where the story is going, I've already figured it out. All right. So a long time ago, right? I believe it was the 50s. I could be wrong on that, but somewhere around that time, in a cave in the Dead Sea, a shepherd found some jars. And obviously you find something like, ooh, what's inside the jar? Opens up the jar and they find
The Bible.
pieces of manuscript that are rolled in called a scroll. And the scrolls are kind of not in the best shape. Okay. And as he basically he gets somebody smarter than him to figure out what's going on, they find out literally he's found a copy of the Bible, not the New Testament, but the Old Testament. It is literally, as at least up to this current date, it is the oldest known version of the Bible that we have. It was found in next to the Dead Sea. These are called the Dead Sea Scrolls. Now, the Dead Sea Scrolls, here's an open one. And when you I can't read this, of course, it's in Hebrew, but the Dead Sea Scroll is readable text. And when they read it, like, hey, look, it's Genesis, it's Exodus, it's Psalms. It was literally a copy of the Old Testament. Important, critical, because for researchers, they were like, wow, we can now trace back. I mean, they believe it's somewhere between 100 to 300 BC when this was written. So it's, yeah, this is Old Testament, not New Testament. Okay. But it's the oldest version that we have. So not only are religious people interested in the Dead Sea Scroll, but historians to check the accuracy of what's happened to the text over time. Now, the problem or the but here is that most of the Dead Sea Scroll is in literally ruins. Like this is the Dead Sea Scroll. I mean, I showed you the nicest piece there. This is what most of the Dead Sea Scroll looks like. It looks like something that needs to be thrown away because you can't see anything. So what scientists did that do this kind of stuff is they hired some people to put it all together. And so, not astronomers. Well, here's a portion of the Dead Sea Scroll that has been painstakingly put together. You can kind of see there's some writing on it, but most of it still looks like I have no idea what's there. So the problem was they had this incredible find, and they were like, well, we really want to read what's written on it, and they can't read other than a few letters. Right? I have no idea. So here's what they did, and we've studied this in astronomy. Instead of using just normal light, they shined specialized light, different wavelengths, onto the text itself, reflects back into a CCD, and they can read stuff off it because different wavelengths reflect differently off of different materials. So these are all in millionths of a meter, nanometer, and you notice these would all be different colors. When they put it all together, it turns into readable text. This idea that you can look at light using filters or different wavelengths is something that we call image processing. Here's a picture of a famous Rembrandt thing. It turned out that when painters were working on something and they're like, that looks like crap, right? And what they would do is, well, they didn't throw it away. They just painted over it. And it turns out that some really famous paintings using this image processing technique, you've probably seen this before, underneath of it was the old painting. It may have had nothing to do with the original painting, but art historians and investigators have been using this technique to search for hidden pictures, not for hidden meaning, but for hidden pictures underneath old paintings, because that's what painters would do. This is the actual one that stands in the museum. This is what was underneath, because apparently Rembrandt was like, nah, didn't like that one. So he reused it. He recycled. Right? All right. So how do astronomers use this whole process? Well, first and foremost, just like the painting and the Dead Sea Scroll, they're able to erase background noise. You do need to write these ones down. Okay. All right. So astronomers using this process called image processing, it's basically Photoshop, right? Just a different form of it. They can get rid of background noise. All pictures that we take, even with CCDs, will have background noise. Noise introduced either by the object or something in between the object that you're taking an image of and your recording device, or the recording device itself can introduce some, they call them artifacts, something that the device or the process itself creates. Here's a picture. Okay, I can tell there's stars there. You do a little bit of image processing. You sharpen it, you clean things up, you turn into these are all three the same image. See, here's the 4 stars, here's the 4 stars, here's the 4 stars. you can turn it into a much better, cleaner image. Doesn't get rid of everything, but it can get rid of a lot. So the first thing is you can erase background noise. You can compensate for known instrument defects. Okay, we've got the Hubble Space Telescopes with the physical device that holds the secondary mirror, which causes diffraction. So we can use this to get rid of those defects. These are not from best to worst. These are all the same basic images taken at different times, right? We throw it through a process to get rid of those known defects, and you get nice, sharp, clear pictures of whatever it is you're looking for. It's not a blob of blue. It's actually white light and nice fine points. And this image is not actually clear whether it's one or two devices. Once it's cleared up, we can see how many objects there actually are. Erases background noise, compensates for known instrument defects. Why do you not want to click today? Basically, what it does is it makes better images. Okay. Astronomers are all about the data. The data is the image. So if there's something that astronomers can do to produce a better image, they want it. So they use image processing all the time. Quick tangent. We talked about CCDs. This was Bell's question or statement earlier. It turns out that CCD images are always, they're black and white. Like your camera in your phone only takes black and white images, does not take color pictures. A CCD can only take a black and white image, and you're like, but that's not true. Mine takes color. I can take a picture right now, prove you wrong. Well, no, CCDs can only take black and white images. So how do they get the color in your black and white image? Your eye feels good guess, but no. So how, if the CCD only takes black, how does it make color pictures?
There's another microchip.
Maybe you've seen this before, maybe you're not. Okay, can you turn this white light to red?
Yes. You put like.
Say it again.
You put like red tape over it.
You put red tape over it, and it turns the white light red. So guess how your phone camera makes colored pictures? It puts colored tape over the CCD. Literally, like no joke. That's what happens.
So how does it recognize?
But it's made of millions of megapixels, right? So how does it do that? So, well, what they do is they're called mask, and they make a mask. So they have CCDs only make black and white. So they take the pixels, and over the top of the pixels, they put a blue piece of tape. I'm not sure why they need two greens. Someone's going to have to explain that one to me. They use the four, it's three, blue, green, and red. The three colors, and this is why if you ever been a Photoshop person and you pick something, you always get these kind of things right here. That's what they're talking about. Okay. So you take a picture, you basically put together the red color, the blue color, and the green color together, and it makes nice colored pictures. I'm leaving out a lot of details, but that's the basic idea. I bring that up because, turn around, this picture right here, Curiosity, it only has CCDs on it, right? It doesn't have a colored camera. It has a one colored camera, but it's still a CCD, so it's black and white. What we call colored cameras are CCDs that have a mask over it. Well, if you have a mask over it, therefore you're cutting down the light. Astronomers don't want that, which is why most of the cameras on that thing are black and white, because they don't want to have the image cut down. But there are some colored cameras around it. I'm about to stand behind my computer. Just will not click today. And if you look right here on the Curiosity itself, is this little thing. This is a sundial. The sundial thing was kind of a whimsical thing that they made, but they have a calibration object for their colored cameras, their mask that they put on their CCDs. It's a tangent, but it's kind of interesting. Notice around it are all the colors. So when they point their camera that has mask on it, when they look at this, it's supposed to be red. When they look at this, it's supposed to be green. And then they're like, hey, look, we got extra space around that. We could put anything they want. So instead of writing their names, they put naked people, dinosaurs, bacteria, you're sending something to Mars. So what do? You kind of like, well, I'm going to put whatever I think is cool. And for nerds, I mean, for scientists, apparently those are the cool things, right? We'll talk about the spacecraft Voyager. That's the same basic picture that we sent on Voyager, was two human beings standing next to each other. They're naked and they're waving. It's like, come eat me, right? Look, I'm tasty, right?
We know they're naked.
Well, on Voyager, it's the same image for Voyager, and they're dead straight naked. I don't know what rocket? What? It seems kind of okay. DNA, bacteria. I don't know why there's a fern leaf. Dinosaur.
Stegosaurus.
Some astronomer or some engineer was like, I love dinosaurs. Please put a dinosaur on this. We spent billions of dollars to send this to Mars, so some guy can put his pet dinosaur on the darn thing. By the way, my name is on this as well too, and it's on this device. You were able to, when they launched this, you were able to send your name to NASA, and they micro engraved your name on a tiny chip. It's so small nobody can see it, obviously. And my name's on that thing.
How much did that cost?
It was free, so I was like, they're like, send your name in. We'll put it on the Mars rover that's going to Mars. I'm like, yeah, I want in on that. I can't really claim that I can prove it other than I sent my name. Yeah, I probably should have saved that. All right, write this one down, adaptive optics. So we talked about image processing. Astronomers love that. And the second one, equally as large as image processing, is something called adaptive optics. No modern telescope, we're talking about astronomer, not consumer grade. No modern telescope is built without this thing called adaptive optics. Remember, one of the big problems with light is light refracts through different mediums. The sky is full of atmosphere. The atmosphere is at different temperatures, different constituencies as you go out higher in altitude. This is why the stars twinkle. Well, this has been a problem for a long time. I don't know the years that they started making this, but it's recent, say in the last 30 years or so. They started building the mirrors with this thing called adaptive optics. Here's how it works. So at the the place where the telescope is kept, right? Oh, why do you want to mess around with me? Okay, light comes in and hits the telescope. Light has to go through the atmosphere. It gets all wavy and wiggly. Your nice clean image of your star is now all messed up. Well, smart people came up with the following process. What they do is they shine a laser beam straight up. Okay, the laser beam goes up, hits the atmosphere, and some of it gets reflected back, and their telescope can see that reflection. They know what the light should look like, the color of it, the clarity of it, that's diamonds, the color of it, the shape of it, right? They know what the laser beam should look like, and they receive that back through their telescope. It's telescope, so they can see this. So it produces a form of that wavelength that's kind of fuzzy. Well, if you feed that fuzziness into a computer, you can, if you were able to, change the shape of the mirror in order to take into account the fuzziness, and that's what they literally do. All right. So they shine a laser beam up into the sky. There's this thing called a sodium layer that's up in the sky, and no, but the concept of adaptive optics will be okay. The laser beam goes up, hits a layer, and it comes back kind of wavy, right? Computers read this waviness, feed that back into another mirror that's able to change its shape to counteract that waviness. Literally on the back of this adaptive mirror are little tiny motors, and they apply pressure to the mirror, which changes its shape. We're talking about a little bit of pressure, otherwise the mirror would crack, right? But on the back of the mirror, I'll show you a picture of it. Why are you not seeing this? Adaptive optics, right? On the back of this mirror, this is the adaptive optics mirrors, are little tiny motors. The motors push up or pull down on the mirror, and they change, we're talking so slightly, change the shape of the mirror. What happens is they read the waviness of the laser as it strikes the sodium layer, and they change the shape of the mirror to counteract that waviness, And boy, does it produce sharp images. I mean, really sharp images.
So what's the definition?
Adapt, we're getting there, right? If my thing would think. So if you look at the back of the mirror, this is what it basically looks like. Now, most mirrors now are segmented mirrors. So they come in two flavors. Either you have one mirror all together, which have a whole bunch of motors, or you have a bunch of little tiny mirrors, the segmented mirror type, and they change the shape of it. I forget how many they have on the back of the James Webb. So each one of those segmented mirrors has a bunch of little, I forget how many, it was a bunch, not like two, it was a bunch. All right, adaptive optics. So obviously we're looking at, okay, does Pluto have rings?
It could.
Pluto doesn't, but turns out Uranus, Neptune, Saturn, and Jupiter all have rings. This is Saturn. Here's with the adaptive optics turned off. Here's with adaptive optics turned on. I mean, it really, really, really sharpens up the image. No modern telescope doesn't have adaptive optics built into it. Here's Uranus with and without adaptive optics. Clearly, this is a good piece of technology. All right. This lesson, we talked about our eyes. Our eyes don't work very well. Adaptive optics is the process. Ready? The process. Adaptive optics, the process of changing a mirror shape to compensate, process of changing mirror shape to compensate for the effects of the atmosphere on an image.
Effects or effects?
You tell me. Are you affected by that question? Are you affected by that question?
I don't know what the difference.
E, not A.
Wait, effects of the what? Effects of
The atmosphere on the image. Okay.
No.
Well, how much got written?
I got adaptive optics is the process of changing mirror shape.
To compensate for the effects of the atmosphere on an image.
Now, in outer space, the Hubble Space Telescope doesn't have adaptive optics because there's no atmosphere in the way. So we're talking about ground-based astronomy, primarily the optical telescopes.
No, it was worse.
Oh, yeah, Dennis, we had a small break.
Yeah, I said Daniels.
All right. So our eyes don't, this lesson we said, our eyes don't work well in astronomy. They work great. I mean, it's not that the eyes are bad, it's just that there's many problems. So astronomers quickly switched to photography, wet photography, lots of problems with that. So we switched to CCD, which is where we currently stand. And CCD, is, since it's a digital medium, gives us the ability to image process, and it also, well, not CCD, but the fact that we have microprocessors now, we can use this thing called adaptive optics. Good, because I'm done. All right. Yeah, I'm not going to start.
You should look up why there's two green, you have like blue and then two green and then one red.
I should. I did learn this. I can't do this. I've been trying to do this. All right, take your fingers. I can't. Can you cross your two fingers and make them very, like hers? I can't do it.
I can.
So I saw this video on YouTube. So if you rub your nose, this isn't weird, but you rub your nose for a minute, it says it will feel like you have two noses. So now rub your nose. Take your glasses off. Now rub,
It already feels like it. What the heck?
rub your nose one side with that, the other one. No. One hand with your fingers crossed. If you rub like this, they say for a minute, it's supposed to feel like you got two noses. No, not like that. It's gotta be one hand.
I feel like two sides of my nose.
It's a minute.
I feel
I just want to know if somebody does that and whether it's true or not. I couldn't bend my fingers enough to make that happen. supposedly the idea is that
Doing it.
you're used to, if your nose was between your two fingers, it would feel like this. But since you crossed it, your brain thinks that anything that touches that side would be over there, and anything that touches the other side would be over there. Therefore, you have two noses.
Okay.
Does it work?
Did you know most people can't see their nose? And like you only become conscious of your nose when you like phase like
Yeah, I'm like that.
I see my nose all the time and it's in the way.
You got glasses on.
Yeah.
I can't see my nose.
Yeah,
You're
I
not-
You see
always,
my cheeks.
I see my nose
Oh,
always. Always.
Look at your nose.
All right.
Just try it. Come here.
Take your hands.
Wait.
Okay, go like this. And go like this.
Oh, dude, I did this
know.
wrong.
Go like this.
Yeah.
I couldn't figure out which finger was which.
All right.
I don't think I'm doing this right.
Yeah,
I'm just gonna stop.
Take your hands like this.
Go like that.
I did
Flip 'em?
Go like,
You gotta
Go like
figure out
this.
which finger's
Scratch
which.
your hands.
and then cross
And
them
then
like
roll
this.
it.
Roll it in. Roll it in. All right.
Supposed to be right here.
Now I want you to lift that finger.
Oh, God, no.
Which one?
Oh, no.
Oh,
Ah.
I want you to lift this finger.
She's a ray.
Wow. You can do it.
Which one?
I want you to lift that finger.
That one.
The internet is full of it.
But men can't.
That used to happen to me as a kid.
Do you remember the big?
Supposedly you're not supposed to be able to do it.
Well, yeah, I used to.
Yeah,
not be
yeah,
able
that
to,
turd,
but I used
yeah.
to do it
The
somewhat.
center of
Or
the-
maybe it's, you're not supposed to touch. Maybe you're supposed to, okay, try it again. Try it again.
What are we trying to do?
Like this. Now flip it around.
Oh.
Now I want you to lift that finger.
Maybe just-
Ah, that's
Yeah.
good. If you touch it, you can do it, but if you don't touch it, you can't.
Wait, you're gonna tell me you want me to move your leg.
So I want you to move that finger right there. Ah, it is
Wait, this
true.
one?
Yeah, you'll get a second chance. All right, flip it around. Yeah, I want you to move that finger right there. Oh, yeah.
Yeah, I know.
I think that's what the video said.
I wish we had just like a chair. We could like try this. in our body.
All right, that'll be it for today.
Bring it up. Does it have 10 fingers?
I can't.